In this lesson, we'll be defining the inverse trig functions. Now, all three of the main trig graphs fail a horizontal line test. And by that, I mean any horizontal line can be drawn that goes through them an infinite number of times, when really it should only be allowed to go through once. So clearly, all of their inverse relations are going to fail a vertical line test. So they won't actually be functions unless we can restrict the domain on the original function so that then our inverse is also a function. And we're going to do that with each of these three graphs in a very specific way so that we always use the same restriction. Now we've seen that we use this notation y equals the inverse function of x for any inverse function. But specifically, when we're talking about an inverse trig function, something like this, it makes sense to use the same set method of restricting that domain every time because these functions are just things that we use so commonly. I mean, even since year 9 and 10, you've been using this notation every time you wanted to find a missing angle. So let's have a look at how we're going to do it now. Now, it makes sense that when we restrict the domain, we want as big a restricted domain as possible, but preferably we want to include all the acute angles. So it makes sense to include the first quadrant, in other words, from 0 to pi on 2, or 90 degrees, for all three of our curves here. Then it also makes sense that we need to use a section that's between the stationary points, because remember, we've already considered that if we want the section of our graph that we're keeping to pass a horizontal line test, then we need to be cautious around the stationary points because it's near those that it would fail a horizontal line test, wouldn't it? So for the sine curve here, we can see that we want 0 to pi on 2, but we're not going to want the second quadrant because if we have that, it'll fail the horizontal line test, so it makes sense to come back this way and take the fourth quadrant, the part that's on the other side there of the y-axis. So we end up with a section that is from negative pi on 2 to pi on 2. And you can see how we got it. We took the acute angles and then we said, hey, we can't get that bit, so we'll go backwards and get this other bit. Let's hop over to this graph as well because it's got that very similar shape around the origin. If we're taking the first quadrant, then it makes sense here to keep a continuous section of graph because I can draw the whole thing without lifting my pen and I don't have any discontinuities. It doesn't really make sense to go across the asymptote there. So it makes sense to have, again, the fourth quadrant and the first quadrant for the tan curve. For the cosine curve, we can't do that because if we take the fourth quadrant, we're going to fail the horizontal line test. So it makes sense to take the next quadrant, the second quadrant, which is going to go down here. So you can see here that I've restricted the domain for these two from negative pi on 2 up to pi on 2, and the same over here. And for this one, we're restricting it from 0 up to pi. Now, rather than memorizing those restrictions, memorize the reason that we're making the restrictions because that's something you can always come back to. We want the first quadrant because that's the simple, straightforward part that we always find our related angles with. And then we want the section that's going to be continuous and not cause us to fail a horizontal line test. So let's start with this graph. Now we say y equals the inverse sine of x. That's how you read that. Y equals the inverse sine of x. Now, importantly, this graph is not just the inverse relation of y equals sine x, okay? It's not that. What it is it's the inverse function. Now, straight away, how can I tell it's a function? Well, it's using that function notation, that inverse function notation with the little negative one there. So this graph, y equals inverse sine x, is actually the inverse function of just the restricted section that we're using of y equals sine x, not the whole thing, just the restriction of y equals sine x between negative pi on 2 and pi on 2. In other words, between negative 90 degrees and 90. Now you can work in radians or you can work in degrees with these things. I've picked radians here, but you could just as happily have negative 90 and 90 degrees in there, and you could put those same things on your graph. Now, what we can see here, if we jump straight to the graphs, this is the graph of the restricted section of y equals sine x, where it's been restricted to between here and here. And you'll notice that it's actually almost horizontal there, or it goes right until it is horizontal, and that's where it stops, right on the horizontal stationary point there, the turning point. So it's horizontal at its endpoints, and we can see that the domain is between negative pi on 2 and pi on 2, and the range is from 1 down to negative 1. So once we then reflect that around the line y equals x, and basically switch the domain and range switch the x and y values, this is our new graph, which we need to label y equals the inverse sine of x. And you can see that its x values go between -1 and 1, so that's its domain. And its y values go from -π/2 right up to π/2, so that's its range. So they've switched domains and ranges. And you can see that here where the endpoints are horizontal, the endpoints of this one are actually vertical. Okay, it's not a perfect graph, but you can see there that's meant to be vertical. We can also see that this graph is always increasing. So it never actually goes downhill. The gradient is positive all the time. Okay, now it doesn't go on and on forever and ever, up this way and down this way. That's it. It has an endpoint right here and right here, and that is the inverse function, y equals the inverse sine of x. Now you can graph it. If you were to graph here the line, oops, that was a bit dodgy, the line y equals x, what you'll find is that here our curve always stays below the line, and here it stays above it. So once we then make that reflection around the line, what you'll find is that it looks sort of like that and like that. And I could have actually drawn this one on top of this curve here so that you see that symmetry around that line y equals x. Now, whenever we're faced with new notation, it's tempting to want to kind of read it backwards. And actually, this is a really smart thing to do, and it's a good skill to make sense of things. So it's natural to have a look at this and want to say, okay, what does this really mean? Well, it means that the sine of y is x. And I would call that reading it backwards. So I've written here, you can read the formula backwards, and that's a good idea. It's a good way to make sense of it. Y equals the inverse sine of x actually means that the sine of y is x. Now that's okay, but word of caution, as long as you know that due to the restricted domain and range, there's actually only one y value that satisfies any given x value in this. Now, why is that? Well, because by definition, this function doesn't go on and on forever. It's just this bit. And you can see that we've got both positive and negative values of x and y. So by covering the fourth quadrant and the first quadrant, we've covered the fact that the sine of an angle could be negative, in which case it'll be an angle that's over here. It'll be a negative angle. And so that basically allows us to only have one answer for any question that's in this sort of form. If we know x, we can find y, and if we know y, we can find x, and there's actually only going to be a one-to-one arrangement between those two. So if we're faced with an equation to solve like this one, we've already learned how to do this, and we know that if we're just asked, hey, the sine of something is a half, what could the something be? There's an infinite number of angles that could fit the bill here and be the answer. So we come up with 30 nice and easily, and curiously, we often put this into our calculator, don't we? Because our calculator, if we're in degrees mode, will spit out 30 degrees. If we're in radians mode, it'll spit out pi/6, which might be hard to recognise. But we've learned how to put this into our calculator. But we've also learned that 30 degrees is not the only answer to this equation. There's multiple answers. We've got a second quadrant answer, and then we've got more first quadrant answers. We can keep on adding 360 degrees to those answers to generate more, and in fact they go back this way as well. We can generate more by subtracting 360 degrees, and then we can generate more answers by adding or subtracting 360 degrees to the second quadrant answer. So there's many solutions to that, but this equation, which looks the same, it looks like it's just written around the other way. The sine of x is a half. It's effectively saying the same thing, but because this one is referring to this sort of arrangement, it only has one solution. So we can kind of forgive the calculator for only giving out one answer because it's actually solving this.